कोई ज्वाइन नहीं कर रहा भाई।
Hello. Since Hello everyone. Since today is National Science Day, so first, before starting this session, I will show you a short video about Earth in 1 minute. Please stay patient, and I will share the screen. So, good evening, everyone. Uh, Hope you all liked the video. Now, I'm Manish Nath from Hex-Star Universe, and I'm going to be your host for this session. First of all, I want to thank everyone for taking their time to join us today. Now, before moving forward with this session, let me give you a brief introduction about what is Hex-Star Universe. So, Hex-Star Universe is basically a space research and education-based platform where students can pursue their careers in the field of space science and technology. We are in a mission of building the biggest community of space science and technology. We also give opportunity to students to work on projects related to space science. Now, coming back to our main event, our topic for today's live talk is demystifying black holes. And today we have Ms. Shivika Lamba with us, and she is a scientist of category A at Stellarion Private Limited. We are really thankful to her for joining us today. And without wasting any more time, I'd like to request her to proceed with today's session. Thank you, everybody, and this is all from my side.
Right. Thank you for that. Am I audible?
Yes, ma'am, you are.
Okay. I'll present my screen. Can you please confirm? Is it visible?
Yes, ma'am, it is visible.
All right. Okay. Good evening, everyone. I'm Shivika, and I'll be talking about black holes today. So to begin with, we would start with the black hole timeline, move on to understanding what do we mean by space-time, and then I would tell you how black holes are categorized according to their mass and what its structure are made up of. And then we'll talk about Hawking radiation, information paradox, thermodynamics of a black hole, and I would end the talk with some recent findings on black hole. All right, so in the year 1796, Pierre Simon Laplace reinvents the original theory of dark stars given by John Michel that surface gravity of some stars could be so strong that not even light could escape from them. Pierre suggested that these largest luminous bodies in the universe may be invisible. In the year 1915, Albert Einstein includes the effect of gravity into his theory of relativity. His equations show that gravity is a wrap in space-time caused by matter. More massive the matter, greater it wraps space-time around it. This provides the theoretical basis for black holes. But before Einstein can solve the equation to his own theory in 1916, Carl Schwarzschild crafted a solution to them. In the year 1931, young Indian astronomer Subramaniam Chandrasekhar defies conventional wisdom and by showing that heavy stars will end their lives in a more exotic state than stars like our sun. In the year 1963, mathematician Roy Kerr shows that massive stars would drag spacetime around them like water swirling around a drain. And in the same year, we had Martin Schmidt discover 3C273, an odd star-like point of light known as a quasar, to be one of the most powerful objects in the universe. His findings led to the realization that all quasars are powered by supermassive black holes at the center of a galaxy. In the year 1967, we had physicist John A. Wheeler bring the concept of collapsed stars to the forefront by coining a new name for them, black holes. And in the year 1971, by combining X-ray, radio, and optical observation from telescopes in space and on ground, astronomers identified the first possible stellar mass black holes, Cygnus X1. Then finally, we have 1974, Stephen Hawking showing us that black holes may not be black after all. They may emit a form of radiation that will eventually cause them to evaporate. All right, so the theory of special relativity and its implications spurred a paradigm shift in our understanding of the nature of the universe, the fundamental fabric of which being was space and time. So before 1905, scientists considered space and time to be completely independent objects. Time could not affect space, and space could not affect time. After 1905, special relativity showed us that space and time are not independent of one another, but they can be mixed into each other and therefore must be considered as the same object, which we denote as space-time. So the consequences of space-time mixing are time dilation and length contraction. So now, if you were to accept the second principle as a fact, that the speed of light in vacuum remains the same for all observers regardless of their motion, then it immediately follows that space and time are not independent. Let's take a look at this with an example. So let's say you're driving a self-driven car and you're in the middle lane. So there are some fast cars passing you in the left lane and you are passing some slower cars in the right lane. So now if all the cars are moving at constant but different speed, then each car has their own inertial reference frame. And if you observe the cars from ground, they will appear to be moving forward. If you choose the reference of the car in the middle lane, then you would say the car in the right lane appears to be moving backward, whereas the one in the left lane appears to be moving forward. And without the road in background, you can't really figure out how fast the cars are moving. The only thing you can tell is how fast they are traveling with respect to one another. But this gets a little problematic when light is introduced. So let's say instead of driving during the night, you're driving during the day. So what do? You turn on your headlights. And if the center car turn on their headlights, they see photons leaving at the speed of light c. Let's consider the headlights of the car in the left lane. Does the headlight coming from the car appear faster due to relative motion? No, that does not happen. Even though the car in the left is moving faster, the photons coming out of the headlights always appear to move at the speed of light c. The speed of light from the middle car will not be c minus x kilometers due to their relative motion. And the same is true for the slower right car. The speed of light is always measured as c. Now, that's a little weird, right? I mean, if Einstein's second postulate that all observers measure the speed of light as a constant is to hold true, then we need some other kind of transformation group so that every observer can see the light beam moving relative to themselves at c. And in order to do such a thing, Einstein realized that our intuitions about space and time must be incorrect, and a new theory is required to describe how all observers move at different speeds can measure the speed of light to be a constant. Curved space-time theory. So now, according to Albert Einstein's general theory of relativity, gravity is no longer a force that acts on massive bodies as viewed by the Isaac Newton universal gravitation. Instead, general relativity links gravity to the geometry of space-time itself, in particularly to its curvature. In classical physics, time proceeds constantly and independently for all objects. In relativity, space-time becomes a four-dimensional continuum combining the three familiar dimensions of space with one dimension of time. To account for gravity and relativity, the structure of this four-dimensional space-time must be extended beyond the rules of classical geometry. In general relativity, space-time is not flat but gets curved by the presence of massive bodies. So what you see on the screen is a simplified 2D surface which gets distorted by the presence of two massive bodies. The distortion caused by each sphere is proportional to its mass. The curvature of space-time influences the motion of these bodies, and in return, the massive bodies move in space-time. So the curvature changes, and the geometry of space-time is in constant evolution. Gravity then provides a dynamic description between matter and space-time. All right, so in order to size up a black hole, you need to be able to deduce how massive it is. And in the 1987 movie Spaceballs, which is actually a parody of the Star Wars franchise, there's a mysterious force known as Schwartz that allows Dark Helmet to battle Lone Star. Upon engaging in battle, Dark Helmet says to Lone Star, "I see your Schwartz is as big as mine." Strictly speaking, the Schwartz has nothing to do with the black hole. But this scene is an easier way to remember that Schwarzschild radius is a measurement of the size of a black hole. The Schwarzschild radius is a physical parameter that appears in Schwarzschild's solution to Einstein's field equations, corresponding to the radius defining horizon of a Schwarzschild black hole. Its characteristic radius associated with the quantity of mass. So we know that there are three kinds of black holes when categorized based on their mass. So that's the stellar mass black hole, the intermediate mass black hole, and a supermassive black hole. A stellar mass black hole is a black hole that gets formed by the gravitational collapse of a single star. They have masses ranging from about 5 to several tens of solar masses. The process is observed as a hypernova explosion or a gamma ray burst. These black holes are also referred to as collapsers. The gravitational collapse of a star is a natural process that can produce a black hole. It is inevitable at the end of a life of a large star when all stellar energy sources are exhausted. If the mass of the collapsing part of a star is below the Tolman-Oppenheimer-Volkoff limit for neutron degenerate matter, the end product is a compact star. That's either a white dwarf for masses that are below the Chandrasekhar limit, or a neutron star, or a hypothetical quark star. If the collapsing star has a mass exceeding the TOV limit, then the crush continues until zero volume is achieved and a black hole is formed around that point in space. The intermediate mass black holes is a class of black holes with the mass in the range of 102 to 105 solar masses. Now, this is significantly more than the stellar mass black holes, but way less than the supermassive black holes. Intermediate mass black holes are too massive to be formed by the collapse of a single star, which is how stellar mass black holes are thought to be formed. Now, but their environments also lack the extreme conditions that are high density and velocity observed at the center of the galaxy that seemingly led to the formation of supermassive black holes. So because of this, there are three postulated formation scenarios for the IMBH. The first is that the merging of stellar mass black holes and other compact objects by means of accretion. The second is the runaway collision of massive stars in dense stellar cluster and the collapse of the collision product into an IMBH. The third is that they are primordial black holes that they were formed during the Big Bang. Now, the supermassive black holes. These are the largest type of black holes, and they have mass in the order of million to billions of times of that of the Sun. The origin of the supermassive black holes remain an open field of research. Astrophysicists agree that black holes can grow by accretion of matter and by merging with other black holes, but there are several hypotheses as to how they were formed. One says that their seeds are black holes of tens or perhaps hundreds of solar masses that were left behind the explosion of massive stars and grow by accretion of matter. Another model says that the first stars, that these large gas clouds could collapse into a quasi star, which would then in return collapse into a black hole. These stars may have also been formed by dark matter halos drawing an enormous amount of gas by gravity, which would then produce supermassive stars with tens of thousands of masses. This quasi-star would actually become unstable to radial perturbations because of electron-positron pair production in its core, and it would directly collapse into a black hole without undergoing a supernova explosion. Okay, now journey into a black hole. So if you were to ever visit a black hole, the first thing that you would notice would be the jets. Now, every supermassive black hole at the center of active galaxies create powerful jets of radiation and particles falling close to the speed of light. So now, when the particle gets attracted by strong gravity, it falls towards the central black hole and it keeps feeding on the surrounding gas and dust. But instead of falling into the black hole, a small fraction of these particles get accelerated to a speed which is almost as great as that of light and gets spun out into narrow beams along the axis of rotation of the black hole. Now, these jets are believed to be the source of the fastest traveling particles in the universe, the cosmic rays. Next, we have the corona, which is a dim cloud-like feature around the black hole's inner disk. Corona are fast-moving electrons that hang out near the black hole. They come in two models, and one is the lamppost model that explains corona to be a source of light that sits close to the rotational poles. Other is the sandwich model that shows corona to be a large cloud that envelops the central disk. Next, we have the accretion disk. That's a disk-like flow of gas, plasma, dust, or any other particle around the astronomical object, in which material orbiting in the gravitational field of the object loses energy and angular momentum, and it slowly spirals inward. Then we have the innermost stable circular orbit, which is known as the ISCO. It is the smallest marginally stable orbit in which a test particle can stably orbit a massive object in general relativity. The location of ISCO, that's the ISCO radius, it depends on the angular momentum, that is the spin of the central object. Next, we have the event horizon. This is the boundary that marks the limit of a black hole. And at the event horizon, the escape velocity is equal to the speed of light. Since general relativity states that nothing can travel faster than the speed of light, nothing inside the event horizon can cross the boundary and escape beyond it, including light. So therefore, anything that enters the black hole cannot be observed from outside the event horizon. Now, finally, we come to the singularity, which is at the center of the black hole, is the ultimate no man land. A place where matter gets compressed down to an infinitely tiny point, and all conceptions of space and time completely break down. But the problem is that singularity doesn't really exist. Something needs to replace the singularity, but we're not quite sure what exactly would replace the singularity. Okay, next is the Hawking radiation. So it's a thermal radiation that is theorized to be released near a black hole's event horizon because of relativistic quantum effects. It is actually named after the physicist Stephen Hawking, who developed a theoretical argument for its existence in the year 1974. Hawking radiation is a purely kinematic effect that is generic to Lorentzian geometries containing event horizons or local apparent horizons. Hawking radiation reduces the mass and rotational energy of black holes and is therefore theorized to cause black holes to evaporate. So, because of this radiation, black holes that don't gain mass through other means are expected to shrink and ultimately vanish. For all except the smallest of black holes, this would happen extremely slowly. So this means that the radiation temperature is inversely proportional to the black hole's mass. So if you were to form a micro black hole, then there's a very good chance that it would stay stable for less than a second. Next is the information paradox. So the black hole information paradox is a puzzle that results from the combination of quantum mechanics and general relativity. Calculations suggest that physical information could permanently disappear in a black hole, allowing many physical states to de-evolve in the same state. But this is a little controversial because it violates the core perspective of modern physics that, in principle, the value of a wave function of a physical system at any point in time should determine its value at any other time. So basically, there are two main principles in play. One is quantum determinism that says that given a present wave function, its future changes are uniquely determined by the evolution operator. Second is reversibility that refers to the fact that evolution operator has an inverse, meaning that the past wave functions are similarly unique. And when you put these two together, then it means that information must always be preserved. Starting in the mid 1970s, Stephen Hawking and Jacob Bekenstein put forward theoretical arguments based on general relativity and quantum field theory that not only appeared to be inconsistent with information conservation, but it did not account for the information loss and stated no reason for it. Specifically, Hawking's calculations indicated that black hole evaporation via the Hawking radiation does not preserve information. Today, many physicists believe that holographic principle demonstrated by Hawking's conclusion were incorrect and that information is in fact preserved. And in the year 2004, Hawking himself conceded a bet he had made, agreeing that black hole evaporation does in fact preserve information. Okay, thermodynamics of a black hole. So thermodynamics of a black hole are quite similar to that of the normal thermodynamic laws. But the four laws of black hole mechanism suggest that one should identify the surface gravity of a black hole with temperature and the area of the event horizon with entropy, at least up to some multiplicative constant. So if you were to consider black holes classically, then they have zero temperature, and that means by the no-head theorem, they would have zero entropy. And so the laws of black hole mechanism would remain an analogy. But when you consider quantum mechanic effects, then you find that black holes emit thermal radiation at a temperature kappa by 2 pi, where kappa is the surface gravity. And from the first law of black hole mechanism, this determines that the multiplicative constant of Stein-Hawking entropy, that would be the horizon area divided by 4. All right, so here are some more black holes. So what I was previously talking about were the Schwarzschild black hole. And there are three other solutions given to Einstein's equation that forms different kind of black holes. So first we have the Kerr black hole, which is similar to a Schwarzschild black hole, but the only difference is that this black hole has spin. Now, Schwarzschild black hole says that no matter what is the amount of spin of the collapsing star, it will never produce a spinning black hole. But Kerr says that it would, and because of that, the structure gets a little different. So instead of having one simple event horizon, it has two different horizons and an area between the two horizons. And this kind of looks like an entry and exit point. So if you were to travel from region 1 and you would actually come out of region 2, but it would mathematically be a different space, and more precisely, it would be an alternate universe. And if we decide to go back to our universe, I mean, you could dive right in, but you would end up in the past of our universe. And Kerr black holes are not like wormholes because they won't collapse because of negative mass energy density to keep it open. And next is the Kerr-Newman black hole. So the Kerr-Newman metric is a solution of the Einstein-Maxwell field equation, and it describes a stationary rotating charged black hole in the asymptotically flat spacetime. Kerr-Newman geometry again has both time translation symmetry and rotational symmetry about its azimuthal axis. And they again have two horizons, which is an inner and outer one, and both of these horizons rotate. Next, we have the Reissner-Nordstrom black hole, which is again a spherical symmetric solution of Einstein-Maxwell field equation, and it describes a non-rotating black hole having mass and charge. The geometry again has two horizons, an inner and outer horizon, and outside the outer horizon, you have a time coordinate. And there's a little space between the outer and inner horizon. And then once you enter the inner horizon, you would again reach time coordinate. Okay, so 2000 onwards. So in 2002, astronomers at Max Planck Institute said that that Sagittarius A is actually a supermassive black hole, which is at the center of the Milky Way galaxy. In the same year, you had a Chandra X-ray Observatory identify double galactic black holes. And in 2004, there was further evidence supporting that Sagittarius A was in fact a black hole. And in 2006, the Event Horizon telescopes began capturing data for black holes. And the first visual evidence of black holes were found in 2012 using the Pan-STARRS 1 telescope. And they published images of supermassive black holes, which was 2.7 million light years away. And that black hole was actually feeding on a red giant star. In 2015, LIGO scientific collaboration detects the distinctive gravitational waves from a binary black hole merging, and the final result of that was a black hole being formed. And moving on, in 2019, you had the first images of black hole from the Event Horizon Telescope, which was the M87. And in the same year, general relativity passed another test. So it showed that general relativity is the best description of how gravity works. And in 2020, there were actually speculations that maybe Planet 9 is not really a planet, but it could be a little black hole that's outside the solar system. But of course, there's no confirmation for that. And in 2021, black holes could be dark stars with blank stars was again a theory put forward, saying that they might not be black at all. So why do we study black holes? We study black holes for mainly scientific purpose, as it would help us in explaining how the universe works and how the universe was formed. And there are also many theories saying that we might be living inside of another black hole. So that, and also black holes can actually be used to test general relativity. And if general relativity was actually proven to be like 100% correct, we could use those corrective terms in like our GPS and get more accurate results. So I think that's why we study black holes. And that's all I have. So if you guys have any questions, I guess you can ask me now. Oh, I see there's some questions in the chat. And I think there's just one that's in the center of our galaxy. It's called Sagittarius A. We don't know if there's another universe inside a black hole. A black hole could just be a portal to like another dimension or something. So we're not very sure what's inside because, like I said, like once you go inside a black hole, you can't really come out of it. So, and plus you can't even observe anything that gets into the black hole. So we don't know, but yeah, there are theories saying that it can act like a wormhole, but you again need negative mass energy to keep that wormhole open. Otherwise, all you have are just two black holes in like two different spacetimes. So, I mean, if that gets proven, then I believe, yes, that they can be a wormhole. Well, see, accretion disk is a disk-like flow of gases. So, like everything, it's kind of like our solar system. If you think of sun as a black hole, then everything that's orbiting around it would like slowly lose energy and just fall into it. So you can orbit a black hole. Is Penrose's diagram? Yes, I believe it is valid. Any proofs on Planet 9? No, I don't believe there have been any proofs. I think they're just many speculations. Is there any, why do Kerr black holes have two event horizons? That's actually a mathematical equation that was written by Kerr. That was one of the solutions. So that's how the solution came out to be, showing that there are two event horizons. I mean, for that, you're really going to have to look into the maths of it. So. Is there a spacecraft that can go inside a black hole? No. I mean, if we're even like technically speaking, anything can go inside, but we don't know what happens when they go inside. I mean, do they just get destroyed? Do they survive it? We're not sure. Why the mass then space-time? Well, since, okay, imagine the universe to be like a sheet, and if you were to add an object to it, then it gets bent, right? So it's kind of like that, right? So did I get all questions? Are there any more? Well, again, I don't know the technicalities because they're all mathematical. So if you really want to look into it, you can go ahead and check. Why don't we have some technology to go inside a black hole? Well, that's because we don't have the technology to travel faster than light. And if light itself cannot escape a black hole, then I think there'll be a slight problem in getting the technology that would travel faster than light and be able to come out of the black hole and tell us what's inside the black hole. So, right. Is that also given by maths? Yes, that is. They're all mathematical equations, to be honest. It's very difficult to find theory on them. You really need to like do a lot of studying to understand those equations, and they're very huge equations. Why nothing can travel more than the speed of light? Well, that's pretty much the limit of the universe. Even if there is something that can travel faster than the speed of light, we haven't been able to catch on to it. So I'm not quite sure as to why there is. Although there is a theory saying that there are tachyons that can travel faster than speed of light, but again, they're all theoretical. There's no evidence to support their existence. Space can travel more than the speed of light. Yes, space can travel more than the speed. That's how we think the universe is expanding. So, any way to be an astrophysicist in a country like India? Uh, yes, I believe there is a way. I mean, at least I'm trying for it. So I'm sure you can do masters in astronomy. I mean, well, astrophysics gets a little more specific, but yeah, I'm sure there is a way. There's also LIGO, so you can look into a little bit of that. And ISRO, as far as I know, hires only people with PhD in astrophysics and astronomy. What are the drawbacks of the black hole, of the backs of theory of relativity? Well, that I'm not quite sure about. You're going to have to search on your own. Any tips for BTech students? Yes. Well, I'm also a BTech student, final year. So basically, just don't lose focus of what you want to do. How can we start being amateur astronomers? Well, you can take up courses and you can start studying on your own. And I'm sure there are like many courses available. So you can start with that. And there's always YouTube. So why do I want to be in astrophysics? Oh, that's because ever since I was a child, this is all I wanted to do. So, have done two courses from Coursera. Would that help? Yes, of course. Coursera would help a lot. So, try doing as many as you can. Does dark matter pokes into black holes? We're not quite sure of that. It probably might. I mean, again, their existence have not really been proven, so it's kind of like hard to say. That's why this whole thing is an open field of research. Yes, of course, I've seen Interstellar. Yes. How can we choose a telescope as a beginner? Probably a refractive telescope would do good for you. So, as a beginner, try starting small and grow as you like. All right, are there any more? So movie, the black hole acts as a wormhole. Why? Like I said, the black hole, if you have negative mass energy to keep that black hole open, it forms a wormhole. That is what the whole Schwarzschild black holes are about. But again, that negative mass energy has not really been found. So is white hole still a theory? Yes, there are theories saying that there might be a white hole at the end of a black hole, but then again, we haven't really found a white hole, so I think it's a little difficult to prove the theory. Any book or course recommendations? Um, okay, well, for books, I mean, for those of you who want to be an astronaut, there's a very good book called An Astronaut's Life to Guide on Earth. And that is very amazing. It's by Chris Hadfield. And there are some books by Neil deGrasse Tyson, I believe. So you can use that, and you can check online courses. You just have to type astronomy online courses, and you'll get a bunch of them. So why modern technology has not proved it yet? Well, that's because it's a hard thing to prove. Mom, can you share your contact info? Yeah, sure. I mean, I think I'll share my LinkedIn profile with you guys. If we send many satellites to other planets and sun, why can't we send a satellite with a camera and join what's inside a black hole? That's because, like I said, nothing that can go inside a black hole be observed from outside, because nothing travels faster than the speed of light. And if light itself is not able to come out of that black hole, I don't really see a point in sending a satellite with a GPS, because those guys will just not be able to send us information back. It'll just be trapped inside a black hole. Is it really possible to travel through a wormhole, as the researcher says it's so small and narrow? Well, I think you get spaghettified in that case. But yeah, I'm sure if you find like a big enough wormhole, then you can possibly travel. I want to become an astrophysics. Please tell me what course to take after 12. Okay, well, I actually took aerospace engineering because there was not many astronomy BSc courses. So you can probably start off with aerospace because that's good. It's a little closer to astronomy. You would learn a lot about rockets and everything, and that's quite interesting as well. So. Will this anyhow help a CS student? I'm not sure what will help a CS student. Can you be a little more clear? Which college did you? I did it with Ramaya University of Applied Sciences in Bangalore. I've taken CS as BTech major. How can I get started with astronomy? In fact, okay. So you can probably start with taking up courses, getting a base in astronomy, and you can actually get into astronomy from any field. It's not very restricted to one thing, and you can try searching for these. Like I said, courses, and there are also some companies that offer a research fellowship kind of a thing. So you can maybe take that because that would help you a lot in establishing a base. Can you send some course link as suggestions? My suggestion would be you just Google it because you'll probably get the best courses out there, and whatever I might like would not be suited to you. So. What's a pulsar? I believe pulsar is it's it's like wait, how do I explain it? It's I think it's this magnetized rotating neutron star. So I believe it produces a lot of electromagnetic radiations. So that is what a pulsar is. What's a quasar? Quasar is like the most brightest thing in the universe, like I said, and these. So like basically sometimes like when the light is like entering a black hole, they sort of orbit it, so that gets really bright. So that. Where can I apply for research fellowship as you advised? One that I know about is the Indian Space Society that I had applied with. And there are a few more. I believe there is SSERD, if I'm not wrong. You can check these two. What's a magnetar? Well, a magnetar is again a neutron star. So it again has really powerful magnetic field and everything. So that. All right. Can we conclude now? Manish, are you there?
Okay, so I think everybody have asked their questions and all their problems are solved now. And thank you, ma'am, for helping us out with this wonderful topic. And thank you, everybody, for supporting us with this diligently supporting us with this session and making this success. And finally, I would like to ask everyone, please, if you can, please switch on your camera once, and we will love to take a screenshot and keep it as our memory. So
Right.
if you can, please,
Right. And Manish, can you share
everyone.
my LinkedIn ID? I think someone's asking
Yeah,
that.
yeah, sure. Yeah,
All right.
I will share that on in the chat.
Sure. All right.
Okay, so we have taken our screenshots. Thank you everyone for supporting throughout the session. And I think we can conclude our session here. And uh, okay, so okay, we can thank you everyone. So we are ending our session here.
Right. Thank you.